And it's a great pleasure for me to introduce our keynote speaker from today, Dr. Willem Heckman. It was not easy to convince him to do the keynote speech, but he's a long-term expert in electric motor design. He has finished his study in 1992 in University of Dortmund in the topic of electrical engineering and mainly electric motor design. Further, he has graduated 2003 at Professor Binder, if I'm right informed, University of Darmstadt. And now he's working almost 20 years at Vitesco, former Continental Chemic in Berlin, as head of electric motor design. And he's a well-recognized and very experienced expert, not only in electric motor design, but also in electric control of electric drives, validation of electric drives. And the topic he introduces today is a bit special. It's not only touching electric motor design, it's also touching the topic of validation of electric motor design. And it gives us a different view, a new view, how you can validate electric motors on a test bench without doing many measurements and losing the view on the simulation model. Please, Mr. Heckman, the stage is yours.
Yeah, thank you, Mr. Cebulski, for the nice introduction. So I'm very impressed how important am I. Huh? Okay, so hello and welcome to my today's presentation, validation of finite element simulations of electrical machines in traction applications. I want to start with a short overview about the contents of my presentation you see here. At first, I want to introduce the base definitions of electrical traction drives, as I assume that some of you are not daily working with traction drives. So it's important to have a good view on the system, what we are caring about in traction drive business. And then I want to introduce the special test sequence with the special impact factors in measuring and validation of these e-machines. The third chapter will be concerned with the evaluation of the optimum operating points. So this is very important to get also over cycles the best efficiencies. And for this, it's absolutely important to have a good tuning of the motor control software to get at each point the optimum operating point. Yeah, and then I will close with a short summary, my view, what is important for the future, and some topics maybe for discussion this evening or tomorrow morning. Yeah, let's start with some base definitions of electrical traction drives. So I have here a short system drive setup. Normally we are driving the e-machine not alone. So the e-machine here on the right side is always combined with an inverter, and the inverter is controlled by a motor control software. And the whole system is fed by a battery. Normally, we have then also a transmission, a mechanical transmission, a gearbox to the wheels then. But it's clear our focus is on the drive system, the combination of inverter, three-phase inverter, and electrical machine. And here, clear to say, so we will talk in this conference a lot about optimization and some topics, and clear to say for an industrial company, for us, the priority one development target is the cost-benefit ratio of complete drive systems. So we are not optimizing an electrical machine. So we want to earn money, so we want to have an optimum system, the combination of power electronics and electrical machine. So this is our priority one target. And if we are talking about or discussing here optimizations, so I have a certain view on this. So cost benefit, this is our optimum. Another point would be our traction drives normally are operated over wide speed ranges. So this is also special compared to industrial drives. So our axle drives normally go up to 16,000 RPM or more, 18,000. And so this makes it special. So also the optimization is then special. So we are not focusing only on the maximum torque, but we have also to focus on the power what we get at 16,000 RPM. So this we have to keep in mind when we are discussing later the optimizations. Yeah, then today we are normally doing the application with permanent magnet machines. And yeah, for the analysis of such a machine type, it's very important to have a view on the single losses of such a type of machine. And yeah, the picture for this can be done by a so-called Sankey diagram. This is a power flow diagram, in this case for the motor mode. And you see here the input power on the left side. So this is the electrical input power, in this case here for the fundamental frequency. Then we have some losses for the stator. We have the ohmic losses, we have the hysteresis losses, and the part we are calling stray losses. Then we are coming to the air gap power, which is combined with the air gap torque, which is normally the result of static finite element simulations. And yeah, on the rotor side, we have also some loss parts. We have stray losses, so for example, eddy current losses in the magnets, and we have mechanical friction losses, PFR. Beside this, we have a parallel path we are calling harmonic losses. So as we know, we are not in the sinusoidal world. We have not sinusoidal voltages, and with this also some ripples on the currents. And these are producing losses, and we are calling these harmonic losses. But this is a parallel path. So this has no contribution to the air gap torque, to the torque itself. These are only losses which we have to handle. And it's very important if we are talking about cycle efficiencies. So WLTP, so is a standard cycle with very low torques and low powers. And for this, the harmonic losses has a very high percentage. So we should not forget this. Normally it's not dominating, but for WLTP, yeah, it plays an essential role. Yeah, then the performance characteristics of e-traction drives, we can have here a sketch of how this normally works. So this is a graph for PU values, so per unit values. So this is for electromachine people very good to handle. So normally you are defining a reference torque, a reference speed, and a reference voltage, and all the values are then normalized with this. And then you get very simple numbers. And you see here the normalized speed, ohmic. So the values are here from 0 to 4. And on the y-axis, you have here the normalized torque and mechanical power. Torque in black and mechanical power in blue. And then you have here the typical characteristics for short term. You are starting with the maximum torque, reaching the maximum power, and then everything is reduced. And this is for short time, 20 seconds or 30 seconds. And the same you can then define for continuous operation. So this is normally in our business 30 minutes or 40 minutes. And here you see you have a little bit less continuous torque and a little bit less continuous power. And yeah, so this is a typical for traction drives. The highest efficiency of such an e-machine is here in the medium speed range and the medium or low torque range. And here we are getting the highest efficiencies, and outside, especially here at high torque, the efficiencies are much, much lower. Okay, so these are the base definitions for your information. So this is not new. Coming now to the e-machine validation. So validation means I want to have a correlation between my simulation and with the measurements. So I want to get the information. How does my simulation fit to the reality? Or how far am I away from the reality? And to answer these questions, I have to consider different topics. At first, my FEA simulations lead to an e-machine design, and this is normally done for ideal and symmetrical geometries, for material data out of the catalog or out of measurements. The motor control has some parameter which I can describe as target parameter. And with this, I'm starting, and then the target of my simulations are to get optimistic, realistic values for torque generation, inductances, and signal losses. And these three values here over a very wide speed range. So as I told you, so normally maximum speed 16,000, 18,000 RPM. So the frequency dependent effects are very dominant in such a system. So this has to be realized also with my simulations. Yeah, and this is a theory, and now we are coming to the reality. And here we have three main impact fields. So we have the sample quality. So normally the electrical machine which are building up is not optimum regarding geometry. So air gap width is not the planned one. Winding head length is not correct. Stacking factor. Then the material data is very important, especially the lamination sheet data has a big impact on the whole situation. Then there is a production impact, and maybe also on the losses, and this has to be considered. The measurement itself is also critical. So the test bench has test bench related losses. We have to keep the e-machine and the inverter on a constant controlled reference temperature, and we have to consider measurement tolerances. The motor control has an impact because we have a speed-dependent offset angle which has to be calibrated, and this has to be done very accurately, so we spend a lot of time for this. If the zero angle or the offset angle is not fitting, then the optimum operating point cannot be achieved. Then, voltage utilization. So what is the maximum voltage which I can get out of the DC voltage is very important. And then the motor control has to realize the optimum operating points regarding MTPA. This means maximum torque per amp. MTPA, so MTPV, maximum torque per voltage, and the minimum loss operation. Yeah, and to get a good validation, so we are normally doing a step-by-step calibration or tuning of the simulations. So we are starting, checking the first numbers, and then going further and further. And so this is our standard procedure. So we are starting normally with a test preparation. So we want to have very accurately measured cold resistances. We have to check the torque offset of the test bench. The rotor position offset angle calibration plays a big role, so we are doing this very accurately. And then we are coming to the second group here, the passive test. Passive test is an operation without inverter, the machine alone. And we are starting with freewheeling with a rotor which is not magnetized. Out of such a measurement, we get a speed-dependent friction losses, which we need for the single loss evaluations. Then we are doing the same freewheeling test with a magnetized rotor, and this can be used for the calibration of the hysteresis losses. Then we are doing a spinning e-machine with short-circuited terminals, and here we get speed-dependent losses with which we can use for the calibration of the skin and proximity factor, as we know that the ohmic resistance of an electrical machine is deeply dependent on frequency. So at high frequencies, the ohmic losses or the copper AC losses, we are calling this, could be very, very high. And this has to be checked by these simple measurements. Yeah, coming now, okay, I missed one point. At the end, we want to measure the optimum operating points. And this is normally done by a set of IDIQ operating points. So we are driving the e-machine current controlled, doing a set of measurements. For example, we have a certain ID of -600 amps, and then adding then an IQ of 0, 100, 200, and so on. And this we are doing in motor and generator operation. And with such a set of measurements, we can then evaluate the maximum performance, the single losses, especially also the stray losses in the rotor and the inductances. And out of this set of measurements, we can use for the calibration, for the tuning of the motor control software, because out of this, we are getting the optimum operating points. So the max torque dependent on current. At the end, to get the good plausible loss distribution, we have to drive heat runs. We want to have heating up the machine and checking where are the hotspots. And this can be put into a thermal analysis. And this thermal analysis leads then to a plausible loss distribution. And this is very important for the feedback to my simulations. Okay, coming now a little bit deeper into the single measurements. As I said before, the freewheeling is the first passive test we are using. This measurements is used to measure the induced voltage. So this is a graph dependent on speed. So this is from 0 up to max speed of 14,000 RPM. And here the black curve, so this is the induced voltage. Normally, the line-to-line voltage peak is the used value because this can directly be compared to the DC voltage level. And this is normally compared then to the planned DC voltage level. And if these induced voltages are below this, an active short circuit is not necessary. So this is a very important information because an active short circuit is a big topic regarding demagnetization risk, and this has to be checked by such a measurement. The other side is to measure the losses, and you see here these curves. These are the freewheeling losses, and one part of these freewheeling losses are the mechanical friction losses, which were measured before. And the difference between both, so these are losses in the lamination stacks, normally I would say 90% in the stator and a few percent also in the rotor as stray losses. And this can then be used for the calibration of my simulated losses. So I can check, see, okay, I have measured here, I don't know, 2 kilowatt losses at 14,000 RPM, and then this can be matched then with the simulated values. The short circuit operation is normally used to check this effect of current displacement in the stator winding. As I said before, it's deeply dependent on frequency, and normally we are measuring the short circuit current over the whole speed range, again from 0 up to 14,000 RPM. You see here it's constant over the whole speed range, so the black curve is a short circuit current. And the respective losses are here in yellow. And you see here, I have a constant short circuit current, but the losses are increasing dramatically. So this is exactly the effect we have. So these frequency dependent losses in the stator winding. And yeah, this can be calibrated with such a measurement. And this can then be put into a JMIC simulation and to verify whether everything was done correctly. Yeah, coming then to a very big topic in the e-machine simulation. And these are the characteristics of the magnetics of the lamination stack. So this is a big problem, and this is one of the biggest impact factors on the simulation accuracy. And the reason why I have listed here. So normally we are needing material data from the lamination material, polarization and specific hysteresis losses. But we have to face 3 big topics. So normally the measurement procedures for these curves are not perfectly fitting to the reality. We can then later have a look into the table here. Then we have essential manufacturing impacts, which has to be considered. So the normal measurement in the Epstein frame has no impact of welding, of punching, of I don't know what. So we have to consider this. And we have to face that we have an unknown quality status of the different lamination stacks. So we have a tolerance band for different e-machines, and this has to be kept in mind. Yeah, the reason why these curves are not fitting perfectly to the reality I've listed here. So normally the measurements were done with Epstein frame or with single sheet tester or with ring core samples, or there are also the possibility to have a stator tester from company Brockhaus, for example. But these measurement techniques are referring normally to alternating fields only, mainly done by one temperature, and they do not have the impact of the manufacturing inside. The impact, what we are normally facing here is annealing, so these thermal working after stamping, then punching, laser cutting, the welding of the lamination stack, the shrinking into a housing, and the insulation quality between the sheets. And you see that these cannot be covered with this type of measurement, because if we are measuring the e-machine, you see here we have not only alternating fields inside the e-machine. So this is normally in the teeth, okay, 90% are alternating fields. But in the yoke, we have, I think, up to 30–40% rotating field. And these are creating much, much more losses than alternating fields. And this we have to keep in mind. And this is the reason why this does not fit very well. And we have the topic that in an e-machine, normally we are not at 20 degrees C, so we are normally in hot status. But this is good for us. The hotter the stack is, the lower the losses are, because the eddy current losses are going down. So this is our reserve. I should say I take always 20 degrees curves, and then I'm conservative, because in under heating, these values are much, much lower. But yeah, the impact out of manufacturing, so this is critical. So punching, laser cutting has an effect on the situation in the teeth. The shrinking has an impact on the behavior of the yoke. So this could be an essential impact. And my proposal, my practical proposal is, due to this, that by modeling the machine in the finite element system, the stator teeth and the stator yoke has to be modeled differently. So we have other material data for the teeth than the yoke. This has to be tuned, and my method is that I take Epstein frame measurements at 20 degrees C and tuning the parameter with the measurements of the freewheeling. So this is very practical. So this is not highly academic, but then you are coming into a target area which is not so bad. So you have to keep in mind, so we are safe. So normally with heating up the stack, so it's conservative if we are taking 20 degrees data. So this method is not so bad, but this is an impact on the accuracy we can achieve. This is clear. Yeah, coming then to important topics, the measurement tolerances normally. So as Mr. Cebulski said, I started my career in '91, and I worked in my first years with measurement techniques of the Stone Age. So there the measurement tolerances were very bad. Deutsche Bahn did not accept torque measurements because it was not accurate enough. So we had to do single losses evaluation for Deutsche Bahn. But today the measurement techniques are extremely good. So don't care about measurement tolerances. The technique is so extremely good. So no impact about this. But we can check what is the situation. So you see here an example. We have here a map, torque, speed, and here you see the accuracy or the efficiency uncertainty dependent on operating point. For a normal example test bench, you see here the best values are 0.2 percentage points. And these are the values if I'm doing, for example, power analyzer measurements, when I get every 0.1 seconds measurement data, then the accuracy is 0.2 percentage points here in the high area. But this can be improved. This can be improved by an averaging. So if you are taking not only 0.1 second value, but I take 20, so I measure over 2 seconds, then I can, by average, improve the situation, and the measurement uncertainties are going then with a factor 1 divided by square root number of measurements. And this is very practical. So we are normally measuring 2 seconds. So in this 2 seconds, the operating point is still constant. No problem about this. We get 20 values doing the average value. And then we are speaking not about 0.1 percentage point measurement uncertainty, but 0.2 divided by square root 20. So it's much, much better with this. And this we should also keep in mind that from the measurement side, with averaging, we can achieve very, very accurate values regarding efficiency of an electrical machine. Okay, so very important, as I said before, are the evaluation of optimum operating points. So here a very, very big gap can be created if we are not within the optimum. So this is, according to my opinion, one of the most important points. And we are normally doing these operating point measurements with such tabular evaluations. So for me, it's very important to have the full numbers for an operating point. So we should have it complete. If it's not complete, I cannot value it because I want to check whether everything is plausible. And we are doing this by redundant evaluation. In Germany, there is an idiom, it's called wer misst, misst, misst. And we have to reduce this and by these redundant evaluations to check whether the operating point is good and plausible. And what do we need? So we need information about the temperature. We need information about the motor control ID IQ. We need information about the DC side, DC voltage, DC current, DC power. Then we need the values for the e-machine itself. So fundamental frequency, then voltage, current, and input power with 3 values, the fundamental value at the fundamental frequency, the RMS value, and both together leads to the harmonic value inside this. And with such a set of numbers, we do not have only the information about the fundamental operating point, but also regarding the harmonic effects. Yeah, on the mechanical side, we have then speed, torque, and mechanical power. And out of this table, we can then have the evaluation of the efficiencies of the single components, for example, e-machine, power electronics, and complete system. And these are values with which we can work and which we can communicate to customers and discuss with customers. For our special analysis, we then have a single loss evaluation, so where all these single losses are summed up. And this would be a topic for the validation of the finite element simulation. We want to check the ohmic losses DC, but also ohmic losses AC means the frequency dependent part of the ohmic losses. We want to have a view on the hysteresis losses in the stator, on the stray losses, harmonic losses, stator, harmonic losses, rotor, friction losses, and also stray losses in the rotor. And these loss paths has to be evaluated, and these can be directly compared to the simulations, and this leads to the message, do I have done the simulations right, or are there some gaps? So very important to check this. Yeah, and such a systematics, so this is base for further evaluation, so I can evaluate motor inductances, phasor diagrams, optimum operating points. But the base of this are always such tables with a systematic ID, IQ, current control, a set of operating points, and out of this I can derive the optima. Yeah, and the optima I can show in some graphics. So as I said before, so with the finite element analysis, we are focusing on torque, on inductances, and on single losses or on losses. And so we have three graphs where we can find the optima. The first graph is the MTPA curve, so the maximum torque per amp. And the systematic you see here, so this is the line current versus torque for the different sets. So for example, the table above has an ID of minus 600 amps with a variation of IQ. So this is this curve. These are exactly the numbers. And then I have here ID minus 500, ID minus 400, and so on. And putting these curves together, you see here, there is a clear optimum. So in the low torque range, it's nearly linear. And then here in the upper torque range, you see saturation and you see additional losses in the rotor. So this is the first topic regarding torque generation. Then we are coming to the inductances, and here we are creating the MTPV curve. So this is maximum torque per voltage. So the systematic is the same. So you see here the curves for ID minus 600. So out of the table on the slides above. And here the other curves. And yeah, with such curves, you can check whether your inductances in your simulations are right. And this is very important for the operating points at high speeds. You can say, okay, my torque fits very well. I have 350 Newton meter, but at max torque, it's very important to have the right inductances. So you should not forget this. It's very important. And also, this is a measurement at 4,000 RPM. This can also be used for checking at 4,000 RPM the performance at 16,000 RPM by having a look what can I achieve with a certain voltage level. And this can be extended to 16,000 RPM, for example. Yeah, and at last, we have to check the e-machine losses. And again, the same situation. So we have the torque on the x-axis and the machine losses, in this case without harmonic losses, so only the fundamental frequency losses. Again, here you see here the curves for ID minus 600 amps, and here the other ones. And you see also here, there is a clear minimum, the dashed red line. And these are the optimum operating points. And you see here how important this is that we are getting this optimum operating points. If we are slightly beside this optimum, we are getting at once 100, 200 watt more losses. And yeah, this should not be. So we have to do these evaluations very carefully and implement this into the motor control software to get a real good value for the efficiencies. You see in such a graph, you can then also draw lines here for certain efficiency values. You see here the value for 96% efficiency, and here the line for 94%. You see here, this is an example e-machine, which has a rather good efficiency here in the medium torque range. And yeah, so this is also a good graph for the discussions with customers to show what is the optimum and what are the optimum values for the total e-machine losses. Okay, so then at the end, I have two additional slides, also as a start for the discussion, maybe this evening. As I said before, these curves before were done for the fundamental frequency component. But we are living in a harmonic world, so we are not feeding the e-machine with sinusoidal voltages, but we have here the time behavior of the voltage here in red. You see here it's a block of needles. And also the current is not optimum sinusoidal, but with ripple. And within, you see here the blue sinus So this is a fundamental component which is inside these. And here in the last graph, you see here the time behavior of the electrical power. You see here, it's absolutely, there is a big DC component inside, but there are many, many ripples on this. And this has to be analyzed. And this can normally be done by Fourier transformation, by checking the frequency spectra for voltage, current, and in this case, apparent power. And then you see, okay, you have here the fundamental component, very big, but you have many, many harmonics here in voltage and also in current, and then also here in power. And you see here two colors. You see the color blue and red. And this should be done for the analysis of the losses, because these are representing positive and negative phase sequences of the different harmonics. And this is for the loss evaluation very important. And this can be derived with the algorithm of symmetrical components, so very easy to do. And then you see here, you have always a pair of harmonics with negative phase sequence and with positive phase sequence. And these excite positive and negative rotating 2p field waves. And this is, I think, the starting point of the analysis of the losses for the harmonics. So we should take out of the measurement as much information as we get. And these analysis of positive and negative phase sequence systems are very important for the loss analysis. I think we can have some more discussions at a coffee or this evening, but this should be the starting point, and this is very helpful. Okay, then coming to my summary. So the targets of the finite element simulations are to produce optimistic, realistic values for torque, inductances, and single losses over wide speed ranges. I have to remark again. The e-machine validation means the correlation between simulation and measurements. And here we have to consider three aspect areas. We have to consider the e-machine quality, means geometries, material characteristic, and manufacturing impacts. We have to consider test bench and test execution. This means we need constant measurement conditions, constant and known measurement conditions, and we have to consider measurement uncertainties. But as I said before, these are not so dramatically bad. And we have to check the motor control software. We need accurate and optimum operating points. And here we have to work very carefully. If we do not implement the optimum operating points in the motor control, we are far away from the optimum situation. The practical guide value for the achievable accuracy, and this is not academically evaluated, so this is my feeling, my stomach feeling. So we are achieving an accuracy of 50 watt. So this seems to be very high. So I know there might be discussions about smaller ranges of losses, but I think facing these topics here, this is an absolutely realistic value. And normally I say we don't need to discuss about 50 watt. So this is within the cloud. So, but the high sophisticated finite element simulations we need, and we need also the techniques. We need this for optimization, and we need this for analysis. So as I said before, we are discussing here the harmonic losses, and the harmonic losses is a big point for WLTP energy efficiency. So we have to know what are these losses, how can I impact these losses, what are the dependencies. And for this analysis, for this loss analysis, we need these techniques. So then it does not matter, we can discuss about 5 watt, but we need the knowledge, and we need the analysis, and we need the optimization. And due to that, it's needed to have these models and techniques. From my point of view, what is needed, what I was wishing, and I told this already Mr. Cebulski, the topics. what I saw, we need to focus on status stray losses. And here, for example, the circulating zero sequence losses in delta connection. So here we saw that with 2D simulations, we are far away from reality. So my feeling is that we can simulate these circulating zero sequence losses only in 3D. So this has to be proven, I don't know. But I know that with 2D this does not work. And this is a big topic because the losses are high and the losses are reducing torque. And I can give an example. So an extreme example for delta connection was 5 Newton meter. So 5 Newton meter you cannot forget. So it's very important. And I would say it's a must to do this in 3D. Also, further stray losses should be checked. Rotor surface losses, I heard this is already in planning or in doing or existing. And I would say everything which is going with eddy currents should be done with 3D. I would say eddy current losses doing with 2D, I would not be confident about this. And yeah, as I said before, harmonic losses, and we are starting here with the analysis phase because it's so important regarding these WLTP energy efficiency things. We have to start this. From measurements, I can say harmonic losses are not ohmic losses, so this is safe. So we have ohmic harmonic losses, but these losses are very small. They are not mainly occurring in the stator lamination. So out of measurements, about many measurements, we saw this, and this should be the starting point for the analysis and for the application of certain simulation strategies. Okay, so with this summary, I'm at the end of my presentation. So I would thank you for your attention, and I would ask you for questions.
Also affect the AC resistance, especially in airplane windings. How would you consider that in the software, or what kind of validation? And later, when you validate every operating point, how would you extract this component?
Yeah, so skin effect in the stator winding, this factor Kr is dependent on temperature, but also on saturation. This you can see, so it's dependent on the ID current. This you can measure, and this is included in our sequence. Now you see we are starting ID minus 600 amps with IQ 0. Then we have also the other ID minus, I don't know. And we have the short circuit current, which is also ID minus, I don't know, 328. And out of this set of measurements, you can check the dependency of these skin and proximity factor dependent on saturation. It's very important. So this are not 50%, but this is 10% or 20%. So not negligible.
Any other question for Dr. Ackman?
I think it's fine. Okay. You mentioned that you split different materials for the yoke and for the state. How do you extract from the measurements which material assumptions you take for teeth?
Okay, so this is practical knowledge. So this is secret for us. It's clear. So we have some practical measures how to do this, but we do not want to present this. It's clear. But this is a good question to give a further remark. So we will talk tomorrow about some innovation ideas. And one innovation idea is to separate teeth from yoke. So we have presented last year a new winding technology, which we are calling endless winding, where we have separated teeth and with a yoke, and the connection is done by dovetail connections. And here you have then the possibility to take other materials. You can take for the teeth very high sophisticated lamination material to get a good situation there. And the yoke, the cheapest lamination material you get. And then it's clear, you have to separate this in simulation. And yeah, as we did this for endless winding, you can do this also with a normal machine, saying, okay, I define a region teeth and I define a region yoke, and yoke has other loss curves, and the teeth has other polarization curves. So this is a direction, and the rest is a feeling.
Okay, maybe one last question as we are a bit already late.
I make it one quick. 50 watts, at which operating point was that, and what is the total losses here? Because you said that the accuracy of total in-machine loss is 50 watts here. But of how many watts?
Independent.
Okay, so because here you mentioned about 16,000 RPM, that's more like automotive max speed. And then if you are in like 6,000 RPM, 30 Newton meter, that's where you have the efficiency matters for you, then 50 watts is quite high number, isn't it?
This map you can show in loss.
Okay.
And then you have here watts, and this 50 watt refers overall. So,
okay.
So it's also here for very low, and for very high, it's independent.
Dependent.
But it's a very rough value.
Yeah.
I want to say it's not 5. It could also be 60. So it's a feeling out of many measurements. So it's an area. It's not fixed 50. It's an area around this.
Yeah, but if it is out of 300 watts, we are talking about 1% difference in efficiency. Then.
Mm-hmm.
Yeah.
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 Okay, thank you. So I suggest to switch to the next presentation. Thank you, Dr. Ackman, for your presentation.